working with equations for functions, we typically say that y is a function of x. And we can use function notation to write this. Writing something like y equal to f of x tells us that y is a function of x, and we are going to call that function f. Oftentimes, we omit the y equal to and we just write f of x. And that's to say we have a function of x, and we're going to call it f. And this shorthand notation helps us abbreviate how we write and evaluate functions. Let's suppose we have a function that takes an input, squares it, and then subtracts 1. In function notation, we would write this as f of x equal to x squared minus 1. I can now easily evaluate this function at different input values. This notation f of 3 means that I should input 3 into the function to determine the output. So everywhere I see an x in my original function, I will change it to a 3. That would give me 3 squared minus 1, or 9 minus 1, which is 8. This is written as f of 3 is equal to 8. This tells me that when 3 is my input into the function, the output of the function is 8. Not all inputs in function notation need to be numbers. So let's think about this function a little bit more. F of x equal to x squared minus 1. We could evaluate something like f of a. This says we need to input a into my function. This would give that f of a equal to a squared minus 1. Since we can't simplify that at all, we simply change the x variable to an a variable. What about something like f of a plus h? In this case, I would change all of the x's to a plus h. So we would have a plus h squared minus 1. We could also write this as a plus h times a plus h minus 1. Foiling then gives us a squared plus ah plus h squared minus 1. Finally, simplifying this a little bit gives us a squared plus 2ah plus h squared minus 1. Next, let's consider the function f of x equal to 3x minus 1. For this one, we know that f of x is equal to 11, and we want to find the appropriate value or values of x that would make this true. This means that we know 11 is the output, and we need to find the appropriate x value. We know that f of x is equal to 3x minus 1, so we change the f of x to 3x minus 1. That gives us 3x minus 1 is equal to 11. Adding 1 to both sides gives us 3x equal to 12. And dividing both sides by 3 gives us that x is equal to 4. So this tells us that the input of 4 would give the output of 11. In function notation, we have that f of 4 is equal to 11. We can do similar evaluations using different representations of functions. Let's consider this function defined by this table. We can see that all the inputs are in fact distinct, so this does represent a function. Let's suppose we want to find the value of g of 2. In this case, we would look at the 2 as the input, and we see that 3 is the output. In this case, we have that g of 2 is equal to 3. Let's suppose we want to know what value or values of x give that g of x is equal to 2. In this case, we're looking at 2 as an output. And that happens in 2 different spots, at 1 and negative 1. This tells us that g of negative 1 is equal to 2 and g of 1 is equal to 2. So in this case, we had 2 solutions. These type of evaluations can also be pulled off of a graph. So let's consider this graph of f of x. Let's suppose we want to know the value of f of 1. This means we go over to 1 on the x-axis, and then determine the appropriate y value, which in this case would be negative 3. So we have that f of 1 is equal to negative 3. Next, let's suppose we want to know the value or values of x that give f of x equal to 0. In this case, we know that y is equal to 0, and we need to figure out the appropriate x values. And we can see that we have 2 of those, at 2 and negative 2. This tells us that f of negative 2 is 0 and f of 2 is equal to 0. So once again, we have two possible solutions.